Hi everyone, this is Prof. K speaking, and today we're going to talk about solubility, which is chapter 11.3. So our learning objectives for today are to describe the effects of temperature and pressure on solubility, or gases and solids in particular. We're going to state Henry's law and use it in calculations involving the solubility of gas in a liquid. So it's a law that will help us talk about solubility of gases and liquids. And we're going to explain the degrees of solubility possible for liquid-liquid solutions, which means we're going to think about how we want to label solutions based on how they mix or how soluble they are in each other. So to review a little bit and also to sort of reiterate the definition of solubility, solubility is the maximum concentration that may be achieved for a solute, or the small component of a solution, in a particular solvent when the dissolution process is at equilibrium. And so what this is saying is if I add some amount of solute to a liquid and it dissolves in that solvent, and I add a little bit more and it dissolves, and then I add a little bit more and it doesn't dissolve, at some point there is the solubility, or the maximum amount of solute I can add to something and have it still dissolve. If something is unsaturated, it's when our solute concentration is less than its solubility. So we haven't hit the point of maximum concentration that we can for solubility. If something is saturated, then a solute's concentration is exactly equal to its solubility. And if we manipulate our experimental conditions very carefully, we can also get what's called a supersaturated solution, where we've exceeded the typical solute concentration that would exist based on the temperature of our system or the pressure of our system. So we've done some manipulation to cause the liquid to, or the solid or whatever, to exceed the solubility that it would normally be able to achieve. And so one of our learning goals is to be able to describe what happens to solubility as you change the temperature of a particular system. And so this first plot is a plot of solubility of solids in liquid as you change temperature. And so what this shows is if sugar is added to water at 0 degrees Celsius, you can dissolve 180 grams of solute or sugar in 100 grams of water. If you increase that temperature to 40 degrees, now we can dissolve 240 grams of sugar in 100 grams of water. So for solids, solubility generally increases with increasing temperature. There are some exceptions. So if you look at this cerium sulfate on the bottom of our plot, if we increase the temperature of this solution, our solubility decreases. But on average, solids typically increase in solubility in liquids as you raise temperature. On the other hand, gases decrease in solubility with increasing temperature. And here, this decrease is partially governed by the fact that solubility for gases is purely determined by their ability to interact with solvents, because there's minimal solute-solute interaction before you try to dissolve that gas into the liquid. And so if you increase the temperature of your liquid, it's easier for those gas molecules to escape the liquid. So the solubility is decreased. And this is actually something we see a lot in our day-to-day life, and also can be particularly dangerous for aquatic communities. Because you can imagine if you increase the temperature of water, the amount of oxygen in that water decreases rapidly. And that's not great if you're a fish who wants to breathe oxygen from the water. So if you ever have a glass that you leave out on the counter of water that was cold and has warmed up, you'll often see these bubbles forming on the glass. And those bubbles are the result of the gas trying to separate from the liquid at the increased temperature because its solubility has been decreased. And this can lead to large-scale fish death because If a particular area, for example, builds a power plant that starts dumping hot water into the river and it raises the river temperature, all of a sudden the oxygen concentration in that water decreases and the fish can no longer breathe. And so a lot of the fish die. And so this is something that people have to be careful about is if you're putting any thermal change into aquatic systems with fish or bacteria or wildlife, you have to be really careful because you can dramatically shift the dissolved oxygen concentration. So this is one way that we can help ourselves remember that solubility of gases decreases with temperature, even though the solubility of solids increases with temperature in liquids. And so this is just something we can sort of think about. But we can actually explicitly quantify how the solubility changes of a particular liquid if we change the pressure of that liquid on our system. And so what this is Henry's law. So Henry's law says that the quantity of an ideal gas that dissolves in some volume of liquid is directly proportional to the gas. And so what this means is if I have my beaker, or if I have a container, and I have two containers, they're identical, even if I can't draw them identical, and we have water and oxygen in our container, what it says is that if I increase the pressure to twice the pressure, it will cause more of the oxygen to be dissolved. And this makes sense logically if you think about it from the perspective of if that oxygen is being pushed harder onto the water, it's more likely that it will go into the water. And so its solubility is higher. And this K here is another K that we use, which is a Henry's constant that depends on the gas identity. So what this means is no matter what, solubility is linearly related to this pressure, or it's related through this constant, but that constant depends on the gas. So oxygen might be more likely to dissolve than another gas is with increasing pressure. And so this helps us predict how if we change the partial pressure of our system that it's feeling, of the pressure of that gas in particular, then we can also change its solubility in a system. Now, I want to warn you that Henry's law breaks down if, as you're adding the gas to the liquid, it's undergoing a chemical reaction with the solvent. So if oxygen is absorbed in this system, it will continue to go into the water because there's more space for oxygen. So this is only trustworthy if the gas doesn't react. So just watch out for this because it can mess with this dependence, which is pretty linear and pretty straightforward. And so we'll use this and the impact of temperature on gases and liquids to help us understand how if we change our system, our solubility might change for a given gas. Whereas for solids, we're just looking at temperature change. And so we sort of have different things that we look at depending on what we're trying to dissolve in a particular liquid. We can also talk about how soluble liquids are in other liquids. And so the language we use for describing liquid-liquid interactions is, are the liquids miscible? And it sounds like mixable, but it's a slightly different language, which is miscible. And it's that these liquids can be mixed in any proportions to yield solutions. And so what this means is if you have two liquids that both can do hydrogen bonding, that if you add a little bit of one liquid that does hydrogen bonding to another liquid that does hydrogen bonding, they're perfectly happy to mix, and vice versa. So you can mix any amount of these two liquids and they always form a solution. They're perfectly miscible, or pretty closely perfectly miscible. And so typically, the liquids that interact have similar polarities and potentially similar types of intermolecular forces. So if you try to mix oil and water, something non-polar with something polar, it doesn't work. That's why the saying oil and water as like personality types that don't mix. So we often summarize this with the quote, like dissolves like, which means similar polarities are happy to mix. Similar polarities, like mixing. And on the other end of the spectrum, we have our oil and our water, which is something that's immiscible. It doesn't like to be mixed in any appreciable way. So if I pour this oil on water, I close my container and I shake it really hard and I force little droplets all throughout the water. And then I put it on the counter, all of the oil will wick itself back up out of the water and it will separate. Even if I try to mix it, they just don't want to talk to each other. They pull apart because they have different polarities and they don't have favorable intermolecular interaction. And so we see these separate layers in our containers. Now, like everything in science, this isn't a binary of miscible to immiscible. We also have what's called partially miscible. And so if something is partially miscible, then that means that the liquids have some amount of solubility in each other. It's not like immiscible where there's nearly zero solubility, and it's not miscible, they're not happy to just completely commingle. Instead, some amount of one liquid is seeping and spreading into the other liquid, but you still see distinct layers. And so in this system, we started with bromine and water, and we mixed them, and a little bit of the bromine colors the water that we have, but ultimately you can still see the bromine and the water layer separate, even if some bromine has colored the water. And so this system is partially miscible, and it has some amount of solubility of the bromine in the water. And so this language will help us describe liquids and liquids depending on how they interact.